Hello, I am Chandan Chattopadhyay, Process Advisor, and I welcome you this video on API 610 12th edition. Let me start with a simple question. If centrifugal pumps are one of the most matured technologies in the oil and gas industry, why do they still fail so often? Pumps have been used for more than a century. Engineers understand their hydraulics extremely well. Yet, in refineries and petrochemical plants around the world, pump failures remain one of the most common causes of equipment downtime. So, what's going on? The interesting thing is that most pump failures are not caused by hydraulic design, they are caused by things like vibration, seal failure, shaft deflection, mechanical instability. And that is exactly why standards like API 610 exist. API 610 is essentially the industry's attempt to capture decades of operational experience and translate that into design rules that make pumps more reliable. Today, we are going to explore 12th edition of API 610 and more importantly, understand why the standard evolved the way it did. Imagine you are designing a refinery pump system. You have dozens, sometimes hundreds of pumps. Each pump may be supplied by a different manufacturer. Without a common standard, every vendor would design pumps differently. Different materials, different vibration limits, different testing requirements. That would make maintenance incredibly difficult. API 610 solves this problem by defining a common engineering framework. It standardizes things like mechanical design, allowable vibration levels, materials of construction, testing procedure, but there is another reason API 610 matters, and that reason is reliability. In many plants, pump failures represent a huge portion of rotating equipment downtime. So the standard is not just about buying a pump, it's about reducing operational risk across the entire life cycle of the plant. Core program modules are the redefinition of NPSH, the revision of datum line definitions, and a more refined selection methodology for the preferred operating region, commonly called the POR. Let's now break down this into three key ideas that fundamentally improve how we design and operate pumps. First is NPSH, or net positive suction head. Think of NPSH as the amount of pressure available at the pump suction to keep the liquid from boiling. If the pressure drops too low, the liquid forms vapor bubbles, and when those bubbles collapse inside the pump, they create cavitation. Cavitation is one of the most destructive phenomena in pumps. So, the updated standard redefines how we interpret NPSH to make sure that the pump doesn't just operate but operates reliably without cavitation risk. Let us now see the second improvement. The second improvement involves the datum lines, which are simply the reference points used when measuring pump head, suction pressure, and elevation. If different engineers and vendors use different reference points, the same pump could appear to have different performance values. The updated definition standardizes these reference points so everyone measures the pump performance in the same consistent way. And finally, we have the preferred operating region, or POR. Every pump has a sweet spot where it runs most efficiently and with the least vibration. That sweet spot is near the best efficiency point. The refined POR guidance ensures pumps are selected to that normal operation stays close to this region, which dramatically improves reliability and reduces mechanical stress. So, in simple terms, these updates help ensure that pumps are not only designed correctly but also operated in the conditions where they perform best and last the longest. The standard clarifies the net positive suction head requirement by clearly defining NPSH3 as the point at which pump experiences a 3% reduction in developed head due to cavitation during testing. In practical terms, this means that when vapor bubbles begin forming at the pump suction and start collapsing inside the impeller's passages, the pump's hydraulic performance slightly deteriorates. The 3% head drop therefore provides a measurable and repeatable reference point that manufacturers and engineers can use to determine the suction performance of the pump during performance testing. By standardizing this definition, the specification ensures that NPSH values reported by different vendors are based on the same performance criteria, which improves comparability and consistency during pump selection and technical bid evaluation. In addition to this traditional NPSH3 definition, the updated standard explicitly introduces the concept of NPSHI, or incipient net positive suction head. NPSHI represents the very early stage of cavitation where vapor bubbles begin to form even before a measurable head drop occurs. While the pump may still appear normally at this stage, these teeny vapor bubbles can still collapse violently within the pump passages and cause localized damage to impeller surfaces. This phenomenon is particularly important for high energy pumps where fluid velocities and energy densities are much higher, making components more vulnerable to cavitation erosion. By recognizing NPSHI as a separate parameter, the standard encourages engineers to consider not only when pump performance begins to decline, but also when cavitations first begin to occur. This distinction is especially valuable when designing systems for critical services where even small levels of cavitation can lead to long-term reliability issues such as impeller erosion, vibration, noise, and premature component failure. As a result, engineers are encouraged to provide sufficient suction margin between available NPSH in the system and the required NPSH of the pump, ensuring stable operation and the expected operating range. Overall, the clearer definition of NPSH3 and the introduction of NPSHI represent an important improvement in the standard, helping engineers better evaluate suction performance and design pump systems that are less susceptible to cavitation damage and long-term reliability problems. Let us talk about something that sounds simple but actually matters a lot in pump calculations: the datum line. The datum line is basically the reference point from which we measure suction pressures and calculate the parameters like NPSH. If that reference point changes, the calculated values can also change. For vertical pumps, the updated standard makes an important clarification. The datum line is now defined at the impeller eye, the exact location where the liquid enters the impeller. Why is this important? Because this point represents the true hydraulic entry into the pump. By using the impeller eye as the reference, engineers get a more accurate representation of the suction conditions actually experienced by the pump. For horizontal pumps, however, nothing changes. The datum line remains the shaft center line, just as it was in previous editions. This works well because in most horizontal pumps designs, the suction inlet and impeller are already aligned with the shaft center line. So, the takeaway is simple. For vertical pumps, the reference point moves to the impeller eye for better accuracy, while for horizontal pumps, the shaft center line to be standard reference point. This helps ensure that everyone, engineers, vendors, and operators, is measuring pump performance in a consistent way. Cavitation happens when the pressure at the pump suction drops so low that the liquid actually begins to vaporize inside the pump. Those vapor bubbles then collapse violently, and over time they can damage the impeller, create vibration, and significantly reduce pump life. To reduce this risk, the updated standard introduces stricter NPSH margin requirements. Specifically, it requires that the available NPSH in the system, NPSH A, must exceed the NPSH 3 by at least 1 meter. That extra margin acts like a safety buffer, ensuring the pump operates well away from cavitation conditions. The standard also removes something called the hydrocarbon correction factor. In past, this factor sometimes allowed engineers to reduce the reported NPSH 3 value for hydrocarbon services, but that could make up the pump appear safer than it actually was. Now the rule is simple. Use the real tested NPSH 3 value from the pump test, and the result is a more conservative and ultimately more reliable pump selection. The latest standard introduces a stricter requirement for net positive suction head NPSH margin to improve reliability. A minimum NPSH margin of 1 meter must now be maintained between the available NPSH and the required NPSH, that is NPSH 3. This margin helps prevent cavitation, which can cause vibration, damage to impellers, and reduced pump performance. In addition, the standard now prohibits the use of hydrocarbon correction factors to artificially reduce the NPSH 3 value on the pump data sheet. Previously, some designs applied correction factors for hydrocarbon services to lower the reported NPSH requirement. The updated guideline ensures that actual tested NPSH 3 values are used, leading to more conservative and reliable pump performance. Let us think about how we actually verify a pump's performance. If you only test a pump at one point, say the rated flow, you really don't know how it behaves across the rest of its operating range. But in real plants, pumps rarely operate at just one exact point. That's why the updated standard introduces 9 mandatory performance test points. These points help engineers define entire pump performance curve, not just a single point operating condition. For example, the tests include the shut-off point, where the pump produces maximum head with zero flow. It also includes the minimum continuous stable flow, which tells us the lowest flow where the pump can operate without instability. Then, of course, there is the rated operating point, which represents the normal design condition. And importantly, the standard requires two NPSH3 tests, one at rated flow and another at maximum flow. This helps verify suction performance under different operating conditions. So, instead of relying on assumptions, the pump's behavior is now fully mapped through testing, giving engineers much greater confidence in the pump selection. High Energy Pumps API 610 Annexer O. Annexer O of API 610 specifically addresses high energy pumps which are considered special performance pumps due to their demanding operating conditions. High energy pumps are typically characterized by very high power density, high differential head per stage, or high discharge pressures. These pumps operate under severe hydraulic and mechanical stresses, and therefore the conventional pump selection criteria used for normal services are not considered adequate. Because of these extreme operating conditions, high energy pumps require additional design and evaluation considerations, including enhanced hydraulic design checks to ensure stable operation and to avoid internal recirculation or cavitation damage, stricter mechanical integrity requirements, particularly for impellers, shafts, and casings which are subjected to high stress, improved materials and metallurgy selection to withstand high pressures, temperatures, and fatigue loading, more detailed rotor dynamic and vibration analysis to ensure long-term reliability, additional testing and inspection requirements during manufacturing and commissioning. The objectives of these provisions in Annex O is to reduce the risk of catastrophic failure, improve operational reliability, and ensure that pumps operate in critical refinery and petrochemical services maintain safe and stable performance throughout their life cycle. Let us talk about high energy pump selection criteria, because these pumps operate under much more demanding conditions. In standard pumps, we usually evaluate suction performance using NPSH3, which is the point where the pump experiences a 3% drop in head due to cavitation. But for high energy pumps, that criteria is not always sufficient. Why? Because by the time you see a 3% head drop, cavitation has already started causing damage inside the pump. So the updated standard requires engineers to look at NPSHI or incipient NPSH. This represents the very first moment when cavitation begins to form, even before the pump performance visibly drops. By analyzing NPSHI, engineers can ensure the pump operates safely before cavitation ever becomes a problem. The standard also requires finite element analysis or FEA for critical components like impellers. This allows engineers to simulate stress, deformation, and structural loads under real operating conditions. So, in essence, the new criteria push engineers evaluate both hydraulic behavior and structural strength, ensuring high energy pumps operate reliably even under extreme conditions. In conclusion, the API 610 12th edition engineering program provides critical updates to ensure compliance and reliability excellence in centrifugal pumps. At the end, if you find that you got enough information for 12th edition of API 610 and its evolution from earlier edition, and you are liking this video, then please share it to your engineers group who will be finding useful.